Oh, hey guys, I'm obviously not here today. I have a lesson here. There's a handout somewhere. I left a physical copy in the room. I've also posted it on Haiku. But today we're starting a new unit. This is going to be on the test, so definitely follow this video carefully. Try the homework, and then on Thursday we will take up any questions you guys may have. Just make a quick note too. I've posted problem set and test review on Haiku for the next test. It's next Wednesday. So today, this lesson is probability distributions. We're going to talk about what a distribution is in a moment. And we're going to open this with a discussion about random variables. So a random variable is a variable that takes on values determined by the outcome of an experiment. So its value depends on the outcome of an experiment. For instance, I could say, okay, my random variable x is going to be the outcome of flipping a coin. There's no numerical values there. So let's say rolling a die. My variable could take on any of the values from 1 to 6. So it's random. It's not assigned until an experiment is performed. Today we're going to talk about discrete random variables. We've talked about discrete and continuous in the past. But essentially discrete means there is gaps between possible values. So for instance, one classic example, shoe sizes. I could have a shoe size of 8, 8.5, or 9, but I couldn't have 8.25 or 8.371. There are gaps between possible values. Their test grades are discrete, really. You can get an 87, you can get an 88, maybe you can get some decimals, but you can't get any decimal. You can't have an 87.31218, for instance. Certainly, if you look at the mark out of 50 or whatever, it's discrete. Continuous, there are no gaps between values. So one example of that is height. I could be 170 centimeters. I could be 171, but I could also be 170.1235. There's nothing preventing my height from being that exact value. So there's no gaps. And lots of variables that we do see in nature are continuous. Height and weight, for example. But today we're just going to think about discrete variables. So there are only a finite number of possible values that our variable can take on. And let's look at a frequency distribution here. This is example 1. And I've given you some data about a family, and it's a survey of families, really. And it's the number of liters of milk they consume per week. 4 families consume no milk per week. 1 family consumes 10 families consume 1 liter of milk per week. 18 families consume 2. 10 families consume 3. 6 families consume 4, and 2 families consume 5 liters of milk per week. And question A says, add a column for relative frequency. So you can fill this out. I don't have my tablet today, so I'm going to be typing everything here. Okay, so relative frequency here, we have 4 families. Out of how many families total do we have? 14 plus 18 is 32, 42 plus 8, 50. Okay. So 4 to 50 consume 0 liters of milk per week. You can write that, of course, as 2 or 25 if you prefer. 10 out of 50, which is 1 out of 5, consume 1 liter of milk. 18 out of 50, which is equal to 9 over 25, consume 2 liters of milk per week. 10 out of 50, which is also 1 over 5, consume 3. Here we've got 6 over 50, which is equal to 3 over 25. And finally, 5 liters of milk per week, we have 2 over 50, which is 1 over 25. Great. And that's the relative frequency. Now, the reason I'm making you do this is because I want you to tell me, what does the relative frequency represent? Well, really, let's say we look at this column here, 1 liter of milk per week. This means that if I chose a random family of this group of 50 families, there's a 1 in 5 probability that that family would consume 1 liter of milk per week. So the relative frequency is the probability that a randomly selected family consumes that amount of milk per week. All right, so here we're going to get into more probability. And what we have here, this is actually called a probability distribution. A probability distribution is a table, a graph, or a formula that gives all the possible values of some data, x, and the probability that each one of those could occur. Okay, and I'm actually going to change this to big X here. For discrete random variables, we usually, actually no, sorry, I take that back. Okay, moving on. Now, customarily, we use slightly different notation for probability distribution. So I'm going to rewrite this. So this number of liters of milk consumed per week. And we're going to label it that. We're going to let X be our data values, little x. And we know we can have 0, 1, 2, 3, 4, or 5. I need to put a new row in. Okay. And we're going to let big X be the random variable corresponding to the number of liters per week consumed by a randomly selected family. So big X can take on any of these values, 0 to 5. Okay, and in probability distributions, we typically write P of that big X ends up being equal to little x. So that's the notation typically used for probability distributions. So what is the probabilities here? We have, let's see if I can copy these. Darn, didn't really work. All right, I'll recopy as many as I can. 1 in 5, 9 and 25, 1 and 5, 3 and 25. No, this is not great production value here. I'm going to delete these. There we go. This is a probability distribution. It tells me the probability of every possible data value occurring. Notice that the probabilities here add up to 1. So there's a 100% chance that a student, or a family selected, drinks either 0, 1, 2, 3, 4, or 5. So probability distribution has to cover all possibilities. You could draw this as a histogram if you like, where the most probable number of liters of milk consumed per week would have the highest power. If you're a bit confused with this, please ask me in class on Thursday when I get back. It's hard to draw on this tablet. And let's think of some properties of, I'm going to go, that should be big X's. Okay, so let's read this. For any given value of x, obviously the probability has to be between 0 and 1, just like any probability, any particular value. Mostly they'll always have values less than 1, but they could go up to 1 in theory. And the sum of all the probabilities, because there's a 100% chance of something happening, probability distributions tell you about every possibility. The sum of all the probabilities has to add up to 1. It's very important. So let's look. Here is a probability distribution. This is example 2. Consider here your x values, your possible variables for your discrete random variable are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is the probability that worldwide, if you pick some random cell phone number, they will start with that digit. So for instance, there's a 30% chance that the first digit of a cell phone number will end up being 0.3. There's a 17.4% chance it will end up being a 2, and so on. And okay, here's a question. What is the probability that you pick a first digit and is greater than 5. So this is actually what? The chances that it's equal to, it could be 6, it could be 7, it could be 8, or it could be 9. Right? And we can get the total probability just by adding up all these numbers. So 6 is 0.067, 7 is 0.058, 8 is 0.051, and 9 is 0.045. Okay, and I'll punch these in my calculator. And this is 0.067 plus 8 plus 0.1 plus, and I get 0.221. So worldwide, there's a 0.221 chance that a randomly selected cell phone number starts with a number higher than 5. And to be even more clear, you can, instead of writing all of these out, this is the probability that x is greater than 5. And that's equal to the probability, it's equal to 6 plus 7 plus 8 plus 9. Now, going through here, the expected value, so probability distributions have kind of like what we call an expected value, which is a value that if you were going to keep picking, say in our milk example here, I've recopied it, these are the probabilities in decimal now, that a randomly selected family drinks 0, 1, 2, 3, 4, 5 liters of milk per day. On average, if I kept picking families, on average, how many liters of milk would they consume? And it's probably, look, there's between 1 and 3, there's a 76% chance a family drinks somewhere between 1 and 3. So I expect the average number of liters of milk consumed per family per week would be somewhere between 1 and 3. But we want to find out for sure. And what we actually do here is a weighted average. So the average, we call this the expected value. And then we use two symbols for that. Mu, which you know is average. It's the average of a probability distribution. And also E of x. Those are two accepted notations for expected value. And we see, okay, so weighted average. Here's how we do it. We go 0 times 0.08 plus 1 times 0.20 plus 2 times 0.36 plus 3 times 0.2 plus 4 times 0.12 plus 5 times 0.04. Okay, and now we add those up. 2 plus 2 times. And I get 2.2, which kind of makes sense. Like 2 is the most probable outcome. So our average should be closest to 2, especially because 1 and 3, which are also close to 2, are the second most likely outcomes. In general, this formula for expected value of a discrete probability distribution is given in your formula booklet. It's a little bit ugly, but it's the sum of, the x values in your distribution times the probability of x equals x. So really you just do it the way I just did it. You take your little x values, you multiply them by the probabilities, you do that for each, and you add them up. Okay, let's do one final example. Okay, so now we're going to look at insurance. So here's an insurance company. They charge $50 a year for a plan, and they pay out according to this table. So if you have a serious accident and you suffer total damage, they'll pay you $10,000. And according to their research, there's only one in every 1,000 insurance claims is this type. Major damage, they pay $5,000, and they've concluded that 2 out of every 1,000 claims is this type of damage. And a minor or no damage, they pay 0. 997 out of 1,000 claims are this sort. And the question is, how much money do they expect to pay out in a year? So expected, that should be a clue word. We're going to use our expected value. So expected value of this probability distribution, which you could also write as mu. You don't have to write both, but you do have to write one. It's you multiply the x values times their probabilities and add them up. Plus 0, this one's not going to affect anything. And let me put that into my calculator. 10. And I get 20 bucks. So they expect to pay out 20 and they get 50 from you. So, they make money, and, it might not cost you too much to pay out the 50 bucks, and it will really save you if you end up with total damage. So it's kind of a brief glimpse into how insurance companies can stay profitable. And that's everything you need to know for now about discrete probability distributions. I would love for you to try this worksheet for homework, and we will take it up further on Thursday.